Hello, everyone, and you'll be so happy, I think. I don't know. But no more related rates. So now we're talking about the second part of this chapter as we're approaching almost we've known all of calculus. We don't have that many more concepts to cover. And we're going to be building into something called U substitution, which if you've looked up derivative answers on derivative calculators, anything online, you might have seen this already where they use U's and DU's. And that's what this is that we're going to be talking about right now. But this first lesson is helping you see patterns to help you learn how to do it a little bit more efficiently. So take a look at these five. It'll be very, hopefully these are helpful when you try them yourselves. Undoing the chain rule. So if we want to do the integral of cosine of x squared times 2x dx, you might not even know where to start. But you have to almost imagine working backwards. Because remember, in order to get the integral here, we need an antiderivative. And an antiderivative is a function such that when you take the derivative of it, you return back to where. So I'm thinking to myself, I'm going to need to take the derivative of something to get back to this. Well, I already see that the derivative of x squared is going to give me 2x. So then what I can think about is I'm going to have, and I need to get cosine. So the derivative of what gives me cosine? Well, that's sine. So it's going to be sine. And I'm going to keep x squared. So the derivative of sine is cosine, leaving the inside x squared, and then times the derivative of that is 2x. Well, I think that'll work. Good. And when you're not sure, it's very important that you check all your work. And I hope you do this in the lesson today. So let's see, is that correct? What's the derivative of sine of x squared plus c? Well, the derivative of the outside, leaving the inside alone, times the derivative of the inside, and then the derivative of c is 0. Well, perfect. That is exactly what it needed to be. So it worked out. What about this one? All right, so we need the antiderivative here. So we know that we need a function such that when we take the derivative, we return. Well, what I see here already is that x to the third, when I take the derivative, is going to be 3x squared. So I'm going to need e to the x to the third. Because when I take the derivative of this, the derivative of e to the x third, well, e is nice because it's going to stay where it's at. Because that exponential, you would do natural log first, but you know, natural log of e is 1. So derivative of e is the function itself, leaving the inside times the derivative of the inside, and the derivative of x third would be 3x third. Well, I think that'll work. And then put the plus c since it's an open integral. All right, and again, let's check. So what's the derivative with respect to x of e to the x third plus c? Well, that's going to give me the function itself times the derivative of the inside, which would be times 3x squared, plus 0, of course, with the c. That should be plus 0, by the way. Up there, the derivative of c is 0. And that works out. It's exactly what we should have gotten. Good. So hopefully the pattern I'm seeing here is when I'm trying to take the integral of these more complex functions, I almost have to think ahead and say, is there anything in here where I can see it when I differentiate it, the inside is already part of this? Let's look at c. What's the integral of 5x to the third minus 1 to the third times 15x squared dx? Again, it looks complicated, but I can see here that if I take the derivative of 5x to the third minus 1, that's going to give me 15x squared. So I know I'm going to need this. I'm going to need this, because that will give me the 15x squared when I take the derivative. But this is a polynomial to the third. So then I have to raise it to the fourth when I do the antiderivative, because you add 1. And I have to account for that, because or you can think about it like this. If I take the derivative of this, I'm going to have a 4 in front as a multiple. So I have to account for that by dividing by 4. That'll bring that to 3. And I think that will work. Okay. But let's check again. So if I check, what's the derivative of, and I'm going to keep it, I'm going to write it as 1/4, 5x minus third to the 4 plus c. Well, that 4 comes in front. So you would have 4 over 4, leaving the inside alone. And that drops to the power of 3, and that's good. That's exactly what we should have been getting. Times the derivative of the inside, which is your 15x squared. And then the derivative of c is 0, so that's fine there. Perfect, so that works. All right. So you can see again, by looking at the derivative of the inside, I almost had that, since I found a function such that when you take the derivative of it, it's within that integral, I'm using that function itself, right? X squared got me 2x, so I stuck with the x squared. The 3x squared is from the x to the third, so I had to keep the x to the third. The 5x cubed minus 1 got me the 15x squared, so I had to keep that, or I had to use that for my antiderivative. Okay. Let's look at 2 more complicated ones, and let's see. Okay, cosine of 3x, sine squared of 3x. So is there a derivative of something in here? Well, I know that the derivative, so I see a squared, and I know that by the chain rule, I'm going to have to take the derivative of the inside there. And the derivative sign is cosine. So I think sine I'm going to be using here. So let's stick with the sine of 3x. Because if you take the derivative of sine of 3x, we'll get cosine of 3x. But then because of the chain rule, we're going to have a times 3. So I have to account for that by adding and dividing by 3. And then because it's sine squared, I know that this whole thing has to be to the power of 3. And when I take the derivative of that 3, that would come in front. So I need another 3 on the bottom. So I think I'm going to need 2 3s on the bottom there. One to account for the chain rule of the 3x, and one for the polynomial, raising that to the third power. All right. So let's see if that's it. So I'm going to rewrite this. I think the answer is going to be 1/9 sine of 3x to the, or sine cubed of 3x plus c. I think that's the answer there. And let's see. Yeah, so this one's more complicated, so it's important to check. Okay, so what's the derivative of 1/9 sine to the third of 3x plus c? And hopefully the derivative of this antiderivative returns us to where we're at. So if I rewrite this as sine of 3x to the third, to help you see this, that 3 would come in front, so we'd be at 3/9, leaving the inside alone. Drop that to a power of 2, times the derivative of the inside. The derivative of sine is cosine of 3x, leaving the inside alone, times the derivative of that, which would be times another 3. Okay. Well, let's see. We have the cosine 3x, we have the sine squared of 3x, and then the 3 times 3/9 would have given us a 9/9. So I think this is going to work out for us, where that goes away. So you're going to end up with cosine of 3x, sine squared of 3x. Perfect, and that's exactly what we were hoping we'd get. So again, what you see here, since I knew that the derivative of, since I saw the squared, I knew that this would, I almost have to account for that, and I take the derivative of sine and I'll get cosine. So I kept the sine of 3x, and then I just had to account for all the later parts in it. Okay? And then one more, part E. What's the derivative of x squared plus 4x plus 2 raised to the power of 5/4 times x plus 2 dx? So what am I seeing here? So I see that the derivative of x squared plus 4x would give me a 2x plus 4, and a 2x plus 4 related to x plus 2. Well, if I pull out a 2, that'll work. So this is going to help us out. So I think we're going to need the x squared plus 4x plus 2. And when I take the derivative of this, I'm going to have a 2x plus 4, but I just want x plus 2, so I have to pull out that 2, and I have to account for that. So I'm going to divide by 2. So again, if you hear what I'm saying, when I take the derivative of this, I'm going to get a 2x plus 4, but I want an x plus 2. So it's going to be a 2 times x plus 2, and I have to account for that 2 by dividing by 2 there. And then this is a polynomial of 5/4, so I have to add 1, so then I'll get 9/4. Again, you add 1, which would be 4/4. And then to account for the 9/4, I'm going to have to multiply by 4/9. Because when that comes in front as a times 9/4, I want that to go away since I don't have a constant here. And I think that'll work for us. So if I simplify this a little bit, I think the answer is going to be 4/18 x squared plus 4x plus 2 to the 9/4 plus c. And I guess I could write this as even 2/9 x squared plus 4x plus 2 to the 9/4 plus c. All right, and let's check. This last one, let's check. All right, what's the derivative of 2/9 x squared plus 4x plus 2 to the 9/4 plus c? Hopefully we got this. Or not this, the original function. So that 9/4 would come in front, so we'd have a 9/4 times that 2/9, and then leaving the inside alone, and then you minus 1, which minusing 4/4 would leave us as 5/4, times the derivative of the inside, and the derivative of the inside would be 2x plus 4. Okay. So cleaning this up, I would have 2/4 x squared plus 4x plus 2 to the 5/4. I could pull out a 2 there and write it as times 2x plus 2, in which that 2 times 2 would make that 4/4 And long and behold, notice how if that goes to 1, we get x squared plus 4x plus 2 to the 5/4 times x plus 2. And there you go. So we did it. So this is building into this idea of what we're going to learn with u substitution, where when you look at these more complex integrals, there's a part to it where when you take the derivative of it, its derivative is in the integral, and we can account for that in picking the easier function integrate. So since the derivative of x squared was 2x, we had to keep the x. We had to keep the x squared. Since the derivative of x to the third was 3x squared, we had to keep the x to the third. Since the derivative of 5x third minus 1 was 15x third, we kept the 15x to the third minus 1. Since the derivative of sine of 3x was cosine of 3x, we had to keep the sine of 3x. Since the derivative of x squared plus 4x was x plus 2, we had to keep this part of the integral. And I hope you're picking onto that pattern, okay? And that's going to help us in the next few days and lessons where we start talking about what u substitution is and how we do it. So I'm going to highlight that so you can see it. And there you go. So highlighting all the parts that we had to keep since the derivative of it was in the integral. Right. I hope that makes sense. You definitely have to try it yourself too to see if you can to make sense of it yourself. All right. Good luck. Hope that helps.